Hello, this is the second video of Mathematics for Computer Science. And as much as I want to talk at the second part of the book, which is about structures and number theory, there is a part of the proofs module that I overlooked. Not that I overlooked, but I didn't include in the last video. And this part is a little bit interesting to me that I said, let's make a video about it and leave number theory until I finish it and make a video about it next week. So it's about state machine and invariant principle. And what I mean by that is, for example, in computer science, when we design or build a system, it should be adaptive and dynamic. And what I mean by that, the system needs to handle all type of possible inputs, which mean handle all type of possibilities that the system problem is resolving. And we can abstract such systems that handle all this possible, all this, or that adaptive system that handles these multiple possibilities that exist. So we can abstract it by defining a combination of ensembles or groups, where Q is the set of states that the system can be on, and the sigma is the possible of the inputs that the system digest. And delta is the transition rule that we take depending on the input to transition from state to state. And Q0 is the initial state, while F is the set of accepting final states that the system can be on. So like I said, in each state, the system takes an input and use it to make a transition to another state. And with this mathematical abstraction, we can visualize the system or the machine into a finite ensemble or a finite group. And more importantly, we can prove its correctness. How can we prove its correctness? So by making sure that we model a condition or a predicate for that system, depending on that system, and that predicate or condition uh, whenever it is true, it tells us that the system is in the correct state or it's working properly. So when we have this correlation, then we can have the rule that if P is true, which is the predicate or the condition, then it is equivalent that the system is correct at that state. And from there, we can use the invariant principle uh, by proving that P is invariant through all the states of the machine. We are proving that the machine is correct since P is true through all the states of the possible state that exists on that system. So that's basically the invariant principle. But however, how can we prove this invariance through all the possible states? And here where it comes the induction logic proof that we talked about. So once we abstracted the system and it is math logically, we can use our proofs, for example, induction proof, by proving that the initial state is correct, and from there we can assume an end state to be correct and use that to improve to prove that that P is true through, for example, n plus one state or depending on the context of the system. And from there, we're proving that all possible states that exist, we have the predicate is true. Then the system is correct. Uh, the invariant principle proof should not be used only on finite states, but we should glide it or include the infinite states also. And what I mean by that is we need to have all the infinite possibilities to be proved correct, for example, or the system should handle all the infinite possibilities. And you might have a misunderstanding because what I mean by infinite, I mean, you could say that infinite sets is something impossible since in computer systems, we don't have infinite memory to store all these possibilities, then it is impossible since our memory is finite. But we are working with integers and rational numbers, which automatically means we're working with infinite groups or ensembles. So what I mean by infinite sets, when we're talking about it, we're not talking about storing infinite elements, but we're talking about the possibility to compute or to handle any combination of the infinite states that could exist or infinite elements that could exist. Because we can handle or we can show or calculate any number between 2 and 4, including the rational numbers. We just need the system that can handle all those infinite possibilities or infinite elements that exist between those two numbers. So as a conclusion, I could say while designing any system or machine, it is crucial to abstract it to a mathematical team or a template, not just for the sake of its abstraction or visualization, but to prove its absolute correctness. And what I mean by absolute correctness, we can prove correctness sometimes through implementation where we test all a set of possible inputs that we have. But when I say absolute correctness, this is a concept that I made by myself. I mean, proving it in one logical proof that will conclude from it that your system it will be correct through any element or possibility that exists in this infinite groups or infinite possibilities. So yeah, that's pretty much it what I want to explain. Thank you for watching and see you next time.